Okay, so we're going to talk about the assignment in Learning Set 1 in the Learn About and Practice It section. It's assignment 1-1, always, sometimes, or never, rational and irrational numbers. On that assignment, you'll see a table at the top of the page. One has numbers that are being added, and another has numbers that are being multiplied. We're going to start with the numbers that are being added and talk about those first three questions on the paper that deal with what happens when you add rational and irrational numbers. And so we can use the examples from the table to inform some of the statements that we're going to be thinking about. I've already started the table, right? We have 6 plus 6 to get 12, 6 plus 1/2 to get 6.5, 6 plus 0 to get 6, pretty straightforward. We can do the same thing with 1/2, right? 1/2 plus 6 to get 6.5. 6.5 is another way to write that. 1/2 plus 1/2 equals 1. And 1/2 plus 0 is equal to 1/2. Same thing with 0. 0 plus 6 is 6. 0 plus 1/2 is 1/2. And 0 plus 0 is 0. Those are pretty straightforward. We know how those work. And all of those were examples of a rational number plus a rational number to get a rational result. And so, if we think about some of the statements on the first, in the first problem, it says rational plus rational equals rational. Is that always true, sometimes true, or never true? Well, we can already see cases where it's true. Right here, we have rational numbers adding up to get more rational numbers. So now the question is, can we think of an example where it wouldn't be true? Can we think of an example where a fraction plus a fraction didn't equal a fraction, right? I'm going to write this in red. Is there an example of a fraction plus a fraction not equaling another fraction? Certainly, there are cases where we have something like 1/2 plus 1/2 equals 1, and that would be a fraction plus a fraction to get a whole number, but 1 is still rational. We can still write it as a fraction. We could write it as 1 over 1, or 5 over 5, or 6 over 6, or whatever, right? So that, yes, we have cases where fractions add to get a whole number, but that's still rational. That's still a rational number. And so the answer to this question, is there an example of a fraction plus a fraction not equaling a fraction? No. There's no such example. And so this is a case where, based on our examples and based on what we know about adding fractions, this is going to be always true. Okay? A rational plus a rational will always equal a rational. So now we can start to think about what happens when we take a rational plus an irrational. And we have some examples of irrational numbers, like the square root of 2, or the negative square root of 2, or pi. Those are all irrational numbers. So let's see what happens when we add those to 6 and 1/2 and 0. Well, 6 plus the square root of 2, right? Here it would be helpful to think about, all right, well, what does the square root of 2 equal? Right? What does the square root of 2 equal? The square root of 2 is approximately equal to 1.4, and I think it goes 142, and then it's a decimal that goes on forever. There's no pattern, and it goes on forever. Right? That's what makes it irrational. So if we take 6 plus this decimal, we're just going to get 7.4142 on and on forever without a pattern. So it's like 7.41, right? But it's still irrational. And the same is true if we take 1/2, right? 1/2 is 0.5 plus 1.41, right? That's just going to make it 1.9142. It's still going to be a decimal that goes on forever without a pattern. And so, same thing with 0, right? 0 plus square root of 2 is still square root of 2. It's still irrational. Even if we consider what happens if we take square root of 2 plus square root of 2. Well, now we just have 2 square roots of 2. So it's just this plus itself, which is still irrational. Nothing about the rationality changed. It's still a decimal that goes on forever and ever. And so same thing with the, but here's a case, okay, so here's a case where something different might happen, because we have a negative, right? So we have a negative square root of 2 plus a positive square root of 2. I mean, if we took negative 2 plus positive 2, we get 0. So the same is going to happen here. We're going to get 0 here. So that's interesting, right? Because these are two irrational numbers, square root of 2 and negative square root of 2, but we added them to get a rational number. Okay? So regardless of what happens with pi, it's going to be another irrational result. When we take a rational number plus an irrational number, we will always get an irrational number. And that's true from the examples here. These are all irrational. These are all irrational. That's always true. But when we take an irrational plus an irrational, sometimes you get an irrational number, but sometimes, if they're opposites, you'll get 0. So this is an example where we would have a sometimes. And our example would be, would be right here, right? We got 0. That's not irrational. 0 is a rational number because it can be written as a fraction, 0 divided by any number. And so this is an example where you have an irrational plus an irrational to get a rational. So that's why this is a sometimes, because it happens. Happens sometimes. Okay? Now let's take a look at multiplying. So that was all about adding. We were adding up numbers, and we could continue the table, but we're going to get similar results. So we can now take a look at multiplying. What happens when we multiply? Okay, so we've already started the table a little bit. 6 times 6 is 36. 6 times a half is 3. 6 times 0 is 0. 1/2 times 6 is 3. 1/2 times 1/2 is 1/4, right? We multiply the denominators. 1/2 times 0 is 0. 0 times 6 is 0. 0 times 1/2 is 0. 0 times 0 is 0. 0 times the square root of 2 is also 0, right? Anything times 0 is 0. That's true for rational numbers. That's true for irrational numbers. And so that 0 times pi is 0. So automatically we can start taking a look at this case. A rational times an irrational. 0 is rational. We just multiplied it by 3 irrational numbers and got a rational result. So automatically we can say there's something going on here that we're going to revisit. Let's start with, though, rational times rational equals rational. In the examples that we went over, that's true every time. And we can say confidently that this is always. And we can think about why, right? It's just like the previous problem. If I take a fraction times a fraction, is there ever a case where I don't get a fraction? Right? Like if I take 1/2 times 1/2, I get 1/4. That's another fraction. Even if I did something like 2 over 1 times 3 over 5, right? That's 6 over 5, right? Or if I did 2 over 1 times 4 over 2, right? That's 8 over 4, or I'm sorry, 8 over 2, which is equal to 4. And you could say, oh, the 4 is not a fraction, but like it can be written as a fraction, so it's still rational. And so this is always true. And we can think about why fraction times a fraction will always be a fraction. That makes sense. Now let's dig in some more to these irrational numbers. We already know what happens if we take 0 times an irrational number. What if we took 6 times an irrational number? Right? Well, one way to think about this is if we review back to the decimal, like square root of 2 is an ongoing decimal that continues forever and ever and ever. If we multiply that decimal by 6, all we're doing is adding square root of 2 plus square root of 2 plus square root of 2 plus square root of 2 like 6 times, right? So 6 times square root of 2, that's just square root of 2 plus 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 square root of 2. It's just adding 6 square roots of 2. And we already talked about how adding an irrational to an irrational sometimes is irrational, but in this case, we're not adding the opposites, right? We're just getting more and more square roots of 2. That's more and more of that decimal that goes on forever. So this is still irrational. But now let's take a look at what happens when we take square root of 2 times itself. Square root of 2 times square root of 2. Now there's a couple ways to think about this problem. We can think about the square roots, right? We can think about the what's happening with the square root, right? The square root is the opposite of squaring something. So another way to write this is to write the square root of 2 times itself. Well, that's the same as squaring it. That's the same as squaring it. And so we can think of that as where the square root and the square are inverses of each other, and they're going to cancel each other out, leaving us with just 2 as a result. Another way to think about this is to think about the decimal again. If you type in your calculator 1.4 times 1.4, you're going to get 1.96. Now that's not 2 exactly, but these two decimals aren't exactly square roots of 2. The cool thing here is if you add more and more decimal places, you're going to get closer and closer to 2. So for example, if I do 1.41 times 1.41, I'm going to get 1.98. If I do 1.414 times 1.414, I'm going to get 1.99. And so you can see as we add more and more of those decimals to this never-ending square root of 2 decimal, I'm getting closer and closer to an actual 2. It's getting closer and closer to 2. And so it should, right? Because that's what it actually equals when we take the full square root of 2 times itself. And so this is a case where we have an irrational number times itself getting a rational result. Getting a rational result. And so that makes this case down here another sometimes. Another sometimes. Okay? And here we can look at a rational number like 0. A rational number like 0 times the square root of 2, which is irrational, getting us a rational result again of 0. And so this is another sometimes. Okay, because we have these examples that produce these results. And so we can say with confidence that this sometimes happens because we see it happening. It also sometimes doesn't happen, right? Like in 6 times the square root of 2, that's not rational, that's irrational like we talked about. And we also have cases where you take like pi times pi, right? Well, that's just pi squared. That's just 3.14159 blah, 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 times itself. That's still irrational. Okay, so that's why this is a sometimes and not a never, because there are still cases where you take an irrational times an irrational and you get an irrational. It's just there are also sometimes when you take an irrational times an irrational and you get a rational. And so that's why we can label that as a sometimes. Okay? So the big idea is we use these examples to help us understand the kinds of numbers we could expect to get when we add or subtract or multiply rationals and irrationals together.